Hello. So, continuing with the basics of environmental fluid mechanics, in today's lecture, we are doing assumptions and approximations. So, this topic is equally important as we have studied other topics like governing equations or dimensionless numbers, etc. And the reason why I say this topic is important because environmental fluid flows are usually very complex, and if we want to solve them analytically or even computationally, we need to simplify the problem because it has several components and it is very difficult to solve for all components together. It becomes computationally very expensive, or analytically it is in most of the cases is not solvable, and that is why we need to make several assumptions and approximations to simplify the problem first and then try to get a solution. And among the most popular or most important assumptions and approximations in environmental fluid mechanics are, the first one is called hydrostatic approximation, and the other one is Boussinesq assumption. So these are among the most important ones, but that does not mean that these are the only important ones. There are obviously other assumptions and approximations which are made while solving the problems, but for our course at the moment we will discuss these two, and if needed we can discuss more approximations later in the course. So let's start with the hydrostatic approximation, and to understand that, let us look at these three images of different kind of flows. So the first one that you look at the left is of a gravity current of dust. Okay, so this is a gravity current of, or you can also call it a dust storm. Okay, the second image is of a lava flow, and third one is something that you know very well, that is river flow, right? And in all these cases, one thing that is common is that the horizontal length scale of the flow is much greater than the vertical length scale, right? And to understand that, let's look at it more carefully. For instance, this is the height of the gravity current here, but if you go behind, if you try to measure the length of the gravity current, which we are not even able to see in this image clearly, that L will be much greater than H. It will be extended far behind the view that we have here. In fact, you can also try to see that in case of this horizontal length scale, for instance here, that is also much greater than the capital H here, right? But we generally consider the direction of the flow, and that's why I'm not really considering that as L. And then in case of lava flow, again, if you consider this as H, that is your vertical length scale, you can consider this as the horizontal length scale, and we already see that L is much greater than H. And it's very well known in case of river. If you can see, the length that we are talking about here is like this, whereas the depth might be here, which is much smaller than L, right? So in all these cases, we very clearly see that H is much smaller than L, right? Which also means that horizontal length scale is much smaller than the vertical length scale. Okay. So now by considering this particular fact, we are going to make some assumptions or some approximation. So to be able to do that, let's first start with the governing equations we have. And as we have already seen, to solve any sort of problem, we first try to use or start with basic governing equations, right? And in this case, we can write three different type of governing equations. Assuming a 2D flow, while the flow is 3D, we will for the sake of this approximation, we will consider only 2D flow, and we will write the governing equation as du by dx plus dw by dz is equal to 0, and then rho capital du by capital dt is equal to minus dp by dx del square u, and then the third will be dw by dt is equal to minus dp by dz minus rho g plus del square w. Okay, where this one is the continuity equation, this is Navier-Stokes equation in x, this is Navier-Stokes equation in z, right? So z here is the vertical axis and x is the horizontal axis. Horizontal and z is the vertical axis. Okay, and just to remind you again, this is the simplified equation. We can also write this equation in 3D by considering y direction as well, but here we are just considering the main longitudinal direction and transverse direction. Okay, so now let's start with the continuity equation here, which is which says that du by dx plus dw by dz is equal to 0. This actually means that du by dx is equal to minus dw by dz. Okay, so here we now apply a scale analysis. So this is the information we have from the continuity equation, but now we want to simplify this equation, and we will use a technique called scale analysis. Okay, so what we can do here is we can simply convert this equation into delta u by delta x is equal to minus, or we can actually get rid of minus sign because that's not really important here when we talk about the gradients. Okay, now when we say delta x, and if you are talking about complete length scale, right, there we can just assume that this delta x is equivalent to capital L and delta z is equivalent to capital H, because this is the total length scale we are talking about, right? And delta z is the total height or depth we are talking about. So delta z can be assumed to be equal to h, and delta x can be assumed to be equal to L. And delta u, and now we are, because considering the full length scale, for delta u also we can consider the maximum velocity minus 0, because that is the range, right? And that is why we can assume delta u is simply equal to u, and delta w can be simply equal to w, because that is the we are it is more like we are subtracting the 0 velocity from the given velocity. And that is why now this equation actually reads like delta u by delta W, or let's start with okay, so that can be written as delta x by delta z. And now by considering the other approximation, we can write delta u can as by delta w, and that is now equivalent to L by h, right? So we are approximating delta u to u, delta w to w, and delta x to L, and delta z to h. And because they are all in approximate form, we don't have to write the equal sign, but they are approximately equal to each other. So what information we have here? So now we know that u by w is equivalent to capital H, L by h. But from previous analysis which we saw here, h is much smaller than L, that is this one. So we will use that analysis that we did before. So L by h is much greater than 1. That means your u by w is also much greater than 1. Okay, so if L is much greater than h, that means L by h is much greater than 1, and indirectly u by w is also much greater than 1. Okay, that actually means u is much greater than w, or w is much smaller than u, right? So now we can make an assumption that w is actually insignificant or negligible compared to u. So u is the horizontal velocity and w is the vertical velocity. So w is negligible or insignificant compared to u, right? And that is why we can assume w to be almost equal to 0 for the given flow condition. Okay, so what we are assuming, the horizontal velocity is insignificant for the given flow condition, right? W is almost equal to 0, whereas u is not. So now this is something we are able to make an assumption based on the given geometry of the flow. So now we can use this information into the other equation, and that is the Navier-Stokes equation that we have. So in this Navier-Stokes equation, which is written particularly for the vertical direction, let's copy this equation. Navier-Stokes equation in vertical, which is the z direction. We can make some simplification here, and that will be that w is now equivalent to 0, right? And that is why this must be equal to 0. If w is 0, dw by dt has to be 0. Likewise, del square w is also equal to 0, right? Because w itself is 0. And what is w? That is the vertical velocity. So this means that we get dp by dz is equal to minus rho g. And what is dp by dx here? Dp by dz, that is the pressure gradient in the vertical direction. So what this particular equation tells now, what information it gives, that pressure in vertical direction is dependent only on the hydrostatic force, or the pressure that we have in vertical direction is only the hydrostatic pressure. There is no additional dynamic pressure in the flow. Okay, so this condition that we see, this condition is known as the hydrostatic pressure condition, or you can also call it approximation. Okay, where the pressure in the vertical direction depends only on the static component, not on dynamic component. Okay, and this assumption is particularly applicable. This is applicable when the vertical length scale is very small, such that the vertical velocity is negligible. Okay, so this is an assumption which is usually made in this kind of flows, what we have seen here, such that we get rid of the vertical velocity and we make our problem much simpler than how it was originally there. Right, and now if we have simplified the vertical Navier-Stokes equation, we can also simplify the horizontal Navier-Stokes equation, and that I will leave for you because you have to expand capital du by dt and also del square u. Okay, so that will give you a simplified Navier-Stokes equation in the horizontal direction. Okay, so this assumption or approximation we are going to use in some cases, especially when we deal with a flow with much larger aspect ratio. Okay, so now moving ahead, the next topic or next assumption which is equally important is called Boussinesq assumption, and this is particularly applicable for buoyancy driven flows where flow is happening because of small density differences. Okay, and in this case we see two examples. First one is of plume, and the second one is of a gravity current, right? And what's happening here is in both the cases, let's assume here it's ambient density and outside here is ambient density, and this is the density of plume. Let's call it rho p, and this one you can call rho g, which is density of the gravity current. And in both the cases, rho p, in this case rho p is smaller than rho a, in this case rho g is greater than rho a, but rho p minus rho a or rho g minus rho a, so let's call that delta rho, is not very large. Okay, they are large enough to create the flow, but the difference is not very much. And if you divide this delta rho by the reference density, that is, let's say rho a, that is the ambient density, then you can assume that to be in range of, let's say, is smaller or equivalent to 10%. Okay, or how do you calculate the percent? Basically, rho times 100 is smaller or equivalent to 10%. Okay, so this value here should be equal, should be smaller than 1. So if this value is less than 10% or the difference is less than 10% of reference density, in such situations we make an assumption called Boussinesq assumption. And now let's look at this assumption in more detail, especially in the context of a governing equation. How do we apply this assumption, and why this assumption is important for such kind of flows. So going back to the same governing equation that we used, let's rewrite those equations. So in this case now we will not assume a compressible flow, incompressible flow. We will write d by dx rho u plus d by dz rho w is equal to 0, and rho dw by dt is equal to minus dp by dz minus rho g plus mu del square w. Okay, so this again the same equation. This is continuity equation, and this is Navier-Stokes equation in z direction. Okay, and we are writing again this for uh, 2D flow, and this can also be written for 3D flow obviously. So what happens when the density difference is very small? Alright, we can assume that rho p and rho g are equivalent to rho a when we are considering the effects of density at other places except when it is multiplied with g. Okay, so in this case, this equation, particularly in second equation, we see there is rho here, there is rho here, and also there is mu, where mu is a property that depends on the density. It depends on the temperature, but indirectly depends on the density. So mu is a function of temperature, so indirectly mu is a function of density, right? So now what we see here is when the density difference is very small, we can replace this rho at all places except when it is multiplied with g by a reference density, and in this case the reference density is rho a. And why do we want to do that? Because if we want to consider the density variation, then this problem will become very complicated, right? Because if you can look into these pictures, the rho inside the plume, I'm writing this as rho p, but rho p itself is changing in x and z axis. So for plume, rho p is a function of x and z, and for gravity current, rho g is a function of, so basically rho p and rho g both are changing in space, right, in x and z direction. And now because they are changing in space, when you want to use this rho value in these equations, you have to consider its value at particular given x and y, x and z. And now if you want to do that, this will become much more complicated. This will make your problem much more complicated. So indirectly, these equations that we have here should look something like this. So d by dx rho xz u plus d by dz rho xz w is equal to 0, and rho xz dw by dt minus dp by dz minus rho xzg plus mu del square w, right? So what you see here is rho is actually a function of x and z everywhere, and that makes the problem much more complicated because you have to model the function of rho everywhere, and that creates another a parameter apart from the velocity u and w, and then there is pressure as well. And that is why we want to simplify this problem using Boussinesq approximation, which is applicable when this condition is applied, when del rho by rho is reference density, that density difference is not more than 10%. Okay, in that case, if del rho is not more than 10% of the reference density, then we can neglect the effect of density variation at all places except when it is multiplied with g. Okay, so what it means is, in this equation that you see, we can assume rho x z to be simply equal to rho a, and rewrite the equation, these governed equations are as rho du by dx plus dw by dz is equal to 0, which basically means du by dx plus dw by dz is equal to 0, right? That is the continuity equation. In the second equation, that is the momentum equation, can be written as rho a dw by dt is equal to minus dp by dz this is little confusing, minus dp by dz minus rho ag plus mu w. Okay, and now wait, except this part here we cannot change, because here it has to be considered as rho as a function of x z g. Okay, and now when we simplify it further, the equation becomes dw by dt is equal to minus rho a dp by dz minus rho by rho a g plus nu d square w. Okay, so here what do you see? Rho is the reference density, which can also be called a constant, and rho here is the rho of xz, which is changing in space, right? So this is for Navier-Stokes equation in Z, and now if you want to write that for Navier-Stokes equation in X, then that will become du by dt minus 1 minus 1 by rho a dp by dx plus nu square u. So this is the Navier-Stokes in X, right, where nu here is the kinematic viscosity, okay, which is simply nu by rho a. Okay, so this is what called Boussinesq approximation, where we are trying to simplify the governing equation for this kind of flows which are driven primarily by density difference. So plumes and gravity currents are driven because there is density difference in the system, right? This plume is rising upward, or gravity current is flowing sideward, because in case of plume, the plume is lighter than the ambient, whereas gravity current is heavier than the ambient. Despite the density difference, despite there is density difference, we tend to neglect the effects of density difference except when it is multiplied with g, right? And why do we consider when it is multiplied with g? Because that is the buoyancy force, that is actually what drives the force, right? If we consider that also as a constant, then the flow itself will not happen, right? So in that is why we have to consider the effects of the density difference in case of gravity, but elsewhere we can consider that to be simply a constant. And this assumption is called the Boussinesq approximation or Boussinesq assumption, and this particularly is applicable when the density difference is not very large. If the density difference is very large, then yes, we do have to consider the effect of density variation in the field to be able to model the flow more accurately. But if it is less than 10%, then by neglecting the effects of density, we can still model the flow quite accurately, or approximately to its true behavior. Okay, thank you.